So let's take a look at sort of our parallel problem here. We looked before at calculating the pH of a weak acid. What about the pH of a weak base? Now here the Kb is 1.8 times 10 to the minus 5 of ammonia. And so our reaction is NH3 plus H2O goes to NH4 plus OH minus. And so the Kb is going to be specifically NH4 plus OH minus over NH3. All right. So and that is equal to 1.8 times 10 to the minus fifth. Let's write out our ice table. We have NH3, NH4, and OH minus that we're keeping track of. And so we have 0.4 initially. That's our 0.4 molar ammonia initially. No ammonium and no OH minus. Again, it's actually 10 to the minus seventh, but you know, to a good approximation. So this is minus X, this is plus X, this is plus X, and we have 0.4 minus X is equilibrium X and X. Okay, so we can just plug this in now, right? This looks exactly like the equations we had for calculating weak acids. So we have 1.8 times 10 to the minus fifth is equal to X squared divided by 0.4 minus X. And let's let's assume that 0.4 minus X is about equal to, not X, definitely not X, is about equal to 0.4. Okay, so if we do that, we get 1.8 times 10 to the minus 5 is equal to X squared over 0.4. And so X squared is 7.2 times 10 to the minus sixth. X will be plus or minus, but really the plus is the physical one, 0.00268. And this is very clearly much less than 0.4. It's about 0.5% of 0.4. So it's a good approximation. And this is our concentration of OH. So remember, if we're calculating the pH, we can't just take the minus log base 10 of this, right? Because that would give us the POH. The POH is minus log base 10. OH minus gives us 2.57. So the pH is 14 minus 2.57, which is 11.43. So that is actually what the pH is. It is quite high because this is a moderately, or it's a not too weak base. pH has to be higher.